Okay. So that if f of x is equal to a constant, then f prime of x is 0. Shorthanded notation that the derivative of x to the n is nx to the n minus 1. That the derivative of f plus g is the derivative of f plus the derivative of g. That the derivative of e to the alpha x is equal to alpha e to the alpha x. We also said that the derivative of f times g is the derivative of f times g plus the derivative of g times f. We have said we proved, we actually did prove yesterday that the derivative of f over g is f prime g minus g prime f all over g squared. I'm going to add a few things. So we're going to practice some of these rules today. I do want to add one other rule to this list. Now, I had made a serious argument that, again, we cared about e as our preferred base for the exponential function, right? Now, it is going to be true that some of you are going to be working in your particular disciplines of science, and you're really going to care about base 7. That e is great, but you care about base 7, right? And in the pre-calculus, you had this issue where, lots of things were done with the natural log and with the exponential without using a base other than that. And then that was okay. That somehow your calculator has base 10, it has base e, it does not have base 2.79, right? Why not? Why is that okay? Why is it okay that the scientist who's working on base 3 cannot go to their calculator directly and press log base 3? Why is that okay? Okay, this is good. This is good? Okay, good. We'll figure out why that is. Yeah. You can put it in, right? So what did people used to do? Yes, they used to change the base. That's exactly right. Right? So if you're in log base 3, so if you care about base 3, right, and we only have base 10 or e, then you change the base from e to 10, right? Because, for instance, log base 3 of 15 is equal to what?
Log base 10 of 15 over log base.
Right. Log base 10 of 15 over log base 10 of 3. Right? That's how you rectify that issue. So you can always change the base, right? Questions on that? You remember this, change the base? That's what it's for, right? It answers that question as to why, if you're in one base, you can always switch to the base that we want. And so the calculator could have just programmed e, right? But most calculators have both 10 and e, and now as the so-called fancy calculators, you can put in any base because all they do is use this formula, right? It's easy to program this formula. I bring this up only because we should not be afraid then to talk about the derivative of 10 to the x. So last time we demonstrated that the derivative of e to the x is e to the x. We made a pretty good argument, not a proof, I'll prove this later, that the derivative of e to the alpha x is alpha e to the alpha x. And now I'm going to ask, well, what is the derivative of 10 to the x? Derivative of 10 to the x is equal to, anybody know? Say it again. 10 to the x times the log of what? You say so confidently. That's right. It's 10 to the x times the natural log of 10. Yeah.
Because you said log, and you put an actual log.
Because we're in calculus.
Okay, so but in calculus, it's the natural.
The log is the natural log. Yeah, that's right. That's right. You know what I'm about to say. You see that question mark there?
Why?
Because it hasn't been justified yet. Yeah. Why is that? Yeah. Okay, so that's a claim. Let's go ahead and just demonstrate that. Well, we know that 10, how do I relate 10 back to E? So again, let me just be clear. That is, we don't know 10, we do know E. In order to show this, we relate 10 back to E. How do I write 10 in terms of E? 10 is E to the natural log of 10. 10 is E to the natural log of 10, yes? The E and the natural log cancel because E and natural log are, oh my goodness, that's right. They're inverses, right? Good. So they cancel each other out. So if you put the natural log of 10, you know, the natural log of 10 is the power, the natural logs of powers, right? So the natural log of 10 is the power you need to raise E to in order to get 10, right? And therefore, if I wanted to know the derivative of 10 to the x, well, let's just be very clear here. So therefore, 10 to the x is equal to E to the natural log of 10 all to the x power. I just raise both sides to the x power. Okay. What's the product of these two? What do? You multiply, right? Yeah, you multiply. So then 10 to the x is equal to E to the x, the natural log of 10. Right? So that the derivative of 10 to the x is equal to the derivative of E to the x, natural log of 10. And then now we'll recall something. What do I know about the natural log of 10? What is the natural log of 10? It's 10 is a constant. The natural log of 10 is a constant, right? So we have a rule for that, that the derivative, recall that the derivative of E to the alpha x is E to the alpha x times alpha, right? And so in this case, this thing right here is simply, I should use red, this thing right here is just simply alpha. No matter how ugly it looks, it's just some number, right? So this is equal to, by this rule, E to the x, the natural log of 10, times the natural log of 10. Okay? We just need to remember, my goodness, what was this again? What's that? That's just 10 to the x. So the derivative of 10 to the x is 10 to the x times the natural log of 10. So that is the proof. Of course, you know this has nothing to do with the number 10. That the derivative of 15 to the x is 15 to the x times the natural log of 15. And in general, if a is positive, a is not equal to 1, then the derivative of a to the x is a to the x times the natural log of a. And so again, here's another reason. I mean, this is also the reason why E is nice, because when the base is E, then you don't have this extra natural log thing that you're always multiplying by, right? Because the natural log of E is 1. So today is going to, part of today at least, we're just going to drill. Let's just practice out all these things we've learned so far. Again, I used to use this example, but now, again, you all stay the same age and I just get older, right? The students. So I used to use this Karate Kid, but nobody knows about the Karate Kid anymore. So, but it was a movie where you know about the Karate Kid movie. Which one? See, this is crazy. There's only one Karate Kid. You should ignore whatever the second one was, right? So, but yeah, this guy was trying to learn karate or whatever, right? This is the short, abridged version that just gets to the point I want to make. And he was learning how to do stuff, and he was doing wax on, wax off, right? And then he was like, well, why am I doing this? And then he was about to get his ass kicked, and all of a sudden, he just started using that stuff to figure out how to save his butt, right? And so here, we're in a place where we have all these tools, and it's just like, why are we doing this? Why are we doing this? And again, we're getting all these tools, learning the derivative of all these functions so that we can do some really interesting word problems, right? Where, again, you as a scientist are going to go discover something, and you're going to say, wow, this is modeled by this function, right? You're going to use these functions to model real-world phenomena, whether it's waves or economic forecast or whatever. And of course, you're going to want to know how things are changing, right? So we're going to go through all of them, basically, right? So right now we're at exponentials. Eventually we'll do logs, and then we'll do trig functions, inverse trig functions, hyperbolic trig functions. I mean, we're going to do everything, okay? And along the way, we'll do some interesting applications. Okay, so we're going to add that to the list. Find the derivative. This for sure will be the meatiest part of the test, where I just say find the derivative. This thing could go, here I have to just be careful again about making a fair test. It's an hour and a half, but I would imagine 10 to 15 of these just with everything, right? So we'll start off nicely. A, f of x equals 4. B, f of x equals 4x minus 3. C, f of x equals the square root of x plus x to the 7th minus 4x to the 3rd plus 10. D, f of x equals e to the x plus 5. E, f of x equals e to the 3x plus 6x squared. F of x equals x squared e to the x. I'm testing on the product rule for that one. G, f of x equals x squared plus e to the 3x over 7 minus 2x. And we'll write, well, let's go ahead and put h here. H, f of x equals 10 to the x power. Go, do them. Just do it. You don't need me. We talked about all this at this point. I'll open the floor to questions about any of these. Yes.
How do you want to simplify?
Oh, that's a great question. So let me just take a look. Let's see. Okay. That's great, and I am going to instruct Jessica that that. If I see that, that's good. Yeah. Typical test questions like that. Again, these are the bare bones mechanical things that we'll just need to know how to do. I guess while I'm here, I will also ask some conceptual questions for those who have these bare bones things down. Do we have all of these? Does anyone still need this sheet, this slide? Get all the functions out, and then I can add some conceptual questions. All right, so some conceptual questions I might ask would be something like, here's some ones I've asked in the past. Explain using derivatives that the sum of increasing functions is increasing. Explain why a function with a positive derivative whose graph goes through the origin will never cross again, will never cross the x-axis again. So those are some conceptual questions. I will
If you can explain it in a sentence, can you do that?
I would prefer a sentence. Yeah, I mean, yeah. An explanation should be in sentences. Say it again? So, yeah, so no, either one is fine. Either one is fine. So, this is good. So, I would like to see a proof. Yeah, I would like to see a proof. Yeah, so, I would like to see it. I would like to see it. This is good. Yeah, so a proof is good. A paragraph is good. Either one is fine. Yeah. A proof, I mean, a proof can be in paragraph form. A proof can definitely be in paragraph form. Yeah. There's something you can write, and I would say that is certainly a proof. I'll write some alternative versions of how I could ask this, right? Let f and g be increasing. Show that the function h, which is f plus g, is also increasing. What I just wrote in blue and this first statement in red are the same question. They're the same question.
On the test, would you prefer, like, if you wrote it either way, does it matter if you write it in paragraph or in group form?
as long as it's right. I can't wait to hear what people say. This is good. Yeah, so you get an idea of how, what I'm intending. Let's go back. That stuff is fun. Let's go back and make sure that we have handled these things in green. F prime, 0, question. F prime, 4. 4x is 4. We have yet to do one like this. Actually, we did this in class. Right? This is x to the 1/2, and although I've given you a proof for the power rule that only deals with integers, we are going to use the power rule for fractions as well. The derivative of x to the 1/2 is, you bring the 1/2 in front, and then you subtract 1 from the power. That is the power rule. And you can leave it like that. Go ahead. Thank you. More?
Yeah.
Is this okay or no? Okay. So then this is 1/2 x to the minus 1/2. The derivative of x to the 7th.
7x to the 6th.
7x to the 6th. The derivative of x to the 3rd is 3x squared times negative 4.
Minus 12x squared.
The derivative of 10?
0.
Nothing. Okay. And so the homework on that's due tomorrow deals with the power rule and adding. The derivative of e to the x?
E to the x.
Plus?
0.
Nothing. Absolutely. We already did this. 10 to the x times the natural log of 10. The derivative of e to the 3x is
3e to the 3x.
3e to the 3x. The derivative of 6x squared, 12x. The derivative of x squared e to the x is absolutely uv. Who said that? Thank you. Go ahead.
For h,
Thank you. For h, go ahead.
did you want us to, can we go straight to that, or you want us to like work it out?
No, it's that. Yeah, once we prove a formula, it's over. Just use the formula. Once we prove a formula, that's why we prove it, right? Once we prove that a to the x, the derivative of a to the x is a to the x times the natural log of a, we're going to use that forever. Product rule, u prime v plus v prime u. The derivative of x squared is 2x. The derivative of e to the x is e to the x. The derivative of e to the x is e to the x. And then u is x squared. That's the product rule. They're the same, right? Yeah, it's not going to matter to me. Yeah, anyone who says that, write it this way, yeah, it's a tyrant. She would just be a tyrant. Oh, it's not cool. It's just normal. It's just like being.
My school does that.
Oh yeah,
They're
no.
really specific about.
No, that's just that's. Well, that's about them, not about you, right? They have issues. U over v. Should I be recording this? U over v prime is equal to u prime v minus v prime u all over v squared. It shouldn't matter to a mathematician. Let me say that. Now I really can't be hired at that school now. Okay, so u prime in this case is the derivative of x squared is 2x. The derivative of e to the 3x is 3e to the 3x. V prime is equal to, the derivative of 7 is nothing. The derivative of negative 2x is negative 2. And you use the formula. And you just plug everything in. I will open the floor to questions about this. You know what I'm going to say about this, that I think that everybody can do these things. Just don't make any mistakes. No pressure. Right? No miss minus signs. Right? if everybody knows how to do it, I mean, it's what separates the A's from the B's. Oh, I knew how to do that, or oh, I missed this. Don't miss anything. Just don't miss anything, right? It's my intention to write a test that's an hour and 15 minutes long so that you have 15 minutes to look over everything and make sure that everything is perfect. That, oh, full disclosure, this is good. At the end of this thing, you know, I'm preparing myself to have to write a ton of letters, right? And so I had mentioned earlier about my goal that everyone learn a lot in this class, but also understand that grades are important. And that I had also made a remark just now about how things are getting super competitive. And what's special about this class is that here there is no competition in that sense, that like, but it is going to be competition for you in the future, right? Where tyrants will say that only this percentage of people can get an A in this class. And then, oh my goodness, wait till you see the infighting that comes out of that. Where people won't start talking to other people about what they got for number 7 and just outrageous things like that, right? And so, you know, I mention this to say that, yeah, there is a difference between someone in this context who gets 100 and someone who gets a 92. Isn't that crazy? That's crazy, but that's true. Right? So be right. If you can get 100, get 100. 100, 100, 100, 100, 100. Right? All right. Only because also you just need to give your best effort, right? Okay, anyway. Questions about any of these? I don't think I can give you anything that's crazy, right? I mean, I can give you something that's tedious, but I can't give you anything that's going to, like... Say it again? Yeah, no, there's nothing I can give you that's going to cause you to cry. No. Again, the challenge will be, do you know what this subject is about, right? All right. We'll answer these in a couple ways. I need to figure out how to do a dual screen. I'll need to look at that. Is there a way to do a dual screen here? I want to put a page right next to this. I'll have to investigate that.
I'll do a dual screen.
Yeah, I just want this screen and I want another screen right next to it and this screen to stay up.
Oh, okay.
Yeah, I'll have to investigate that. There should be a way to do that.
There is.
Yeah. All right, F. The last time I put this on the test, it was written in blue. It was the blue formulation of it. Okay, so let's do the blue first. Let F and G be increasing. Show that H, which is the sum of F and G, is also increasing. I'll open the floor. How would you answer this? Or either way, what would you say in paragraph form? What would you say in terms of calculus? Go ahead.
When you answer this question, do you want us to like reprove the stuff that we've already proved?
No. Once we prove something, it's now out there, common knowledge. You can use everything we've shown. Yeah. Please go ahead.
I would show that the derivative of f is always positive and the derivative of g is always positive.
Good. Now you don't have to show that. You can say that because we've already shown. Yeah, we've accepted that. Go ahead.
And then say that the derivative of h is equal to the derivative of f plus the derivative of g. And since the derivative of f is always positive and the derivative of g is always positive, the derivative of h is always positive.
Flawless. That is flawless. That's perfect. That's perfect. Questions on that? Right, I'll write that in just a moment. That is just perfect. Right, so we'll take the, that is exactly what I want mathematically, right? That that formulation is precisely fits the whole narrative of the course. That since f is increasing, that means we'll write it on another page. Since f is increasing, that means that f prime is positive, Right? I've said that so many times. I want you to know that. That's why I've asked. Since G is increasing, G prime is bigger than 0. This here means that I'm using the word above. I put this one time and someone was like, what is that? It's just referencing this. Okay. Then G prime is also bigger than 0. I want to show that H is increasing, which means I want to show that the derivative is positive, but the derivative of H is the derivative of F plus the derivative of G, both of which are positive. And so since H prime is positive, then H is increasing. That is excellent. Excellent. Questions about that? So yeah, this represents the supposed challenge of the test, being able to articulate what you know in a way that is understandable. Paragraph form, anybody?
I wrote the wrong thing. I wrote question.
Okay. All right, the other one. Let me write this one in blue. For how I've written it before. Suppose, let's say let f of 0 equals 0 and f prime is positive. Show that, or explain, I think I say explain why the graph of f.
Does it have to be the origin? Because it could be any point on the graph.
It could be. I like the origin. Yeah. Explain why the graph of f. So usually if an explanation has nothing to do with the point in question, we usually just pick the origin.
Okay.
Yeah. Explain why the graph of f never crosses the x-axis again. This is probably more paragraph form than mathy. How would you explain that? I might say draw a picture that represents this. Draw a picture of this. Draw a picture of a function that goes to the origin with a positive derivative. And by the way, as you try to come up with an explanation of why this is true, you should probably draw a picture because it gives you an idea of why this is true. So draw a picture of a function that goes through 0, 0 with a positive derivative, and then convince yourself why you can't hit the x-axis other than the origin. All up in the floor. Explanations? Why is this true? What does your picture look like? We got 1 point, right? This one goes through here. This, right? That?
No.
Oh, okay. What does it look like? This? Is that okay?
You can, if you want to explain why, you can do the little dip as well.
Is that okay? That's better? Okay, that's better. Okay, okay. Does this seem obvious or no?
The graph.
Say it again.
Or is it, I can't quite word it.
That's why we're here, sister. Yeah, that's why we're here. We gotta word it. So let's talk our way through it. What is it that you want to say? What do you want to say? Go ahead. No, go ahead.
Oh, sorry. So I just said, since the derivative of f is greater than 0, then the function is always increasing, and then to cross the x-axis again, the function would have to be negative because
What would have to be negative?
or the derivative would have to be negative, and so because of the intermediate value theorem, it would have to, it would have to be negative. The derivative would have to be negative to cross it, and so because it's always positive, then it will cross the x-axis.
Okay, you said too much.
Yeah.
That's okay. So yeah, we just need to fix that. Everything before you brought in the intermediate value theorem was perfect. Yeah, you didn't need so again, so when I ask this, again, we're in the context of a test. You want to say the right thing, but you can always say, what have we been talking about, right? So obviously I want you to say, because f prime is positive, f is increasing, right? And it also has to do with how we solve this problem, right? So if it goes to the origin, since f prime is positive, f is increasing, and so on the whole positive real line, and so it's never going to come back down to be 0 again. That's it. I'll take that. That's it. All right. Questions about that? Yeah, so I'm not being super complicated, but again, you should be able to explain it in a way that somebody on the street is like, oh, that makes a lot of sense. Once I know what the translation is, right? It's like you're just translating this, right? So it's like I present this to you in mathematics, and now I want you to see whether you can translate it, right? Because math is just a language, right? And so the only thing that makes me a so-called expert is that I know the language and the translation, and I'm asking you to translate as well, because then that will convince me that you know it. Right? Yeah, I mean, if you don't know mañana, I can't say that you know Spanish. I just can't. I don't believe you. So if you don't know that f prime being positive means that f increases, then I don't think you know calculus. I just don't believe it. Right? And that's just the language of it. Questions about this? So yeah, I'll concoct some more fun ones. You want to do one more?
Yeah.
Okay, okay, good. Go ahead.
About the test, are there going to be more like conceptual problems or like mathematical calculation problems?
That's a great question. So I don't know the answer to that. Usually there are enough conceptual problems to make the difference between an A and a B, right? So that if you got all the conceptual problems wrong, right, I would be deeply disturbed. But if you did all of the calculation problems right, you were probably still going to be, right? So it will make the difference between an A and a B. Yeah. And then frankly, if you just bombed all these all these conceptual things again, then I'm a truth teller. Then if someone asks me about you, I'm saying, oh, this person can do all the calculations, but conceptually, they just didn't get any of it. So yeah, I mean, that's just the truth, right? So, okay, other questions about this? One more, you say? All right. These aren't easy to come up with, but I think I got one. If F and G are positive, the functions themselves are positive and they are increasing, show the product is also increasing. So this is similar. See, now I gotta think of some new ones. You know, I've already done the ones that I've given in the past. So, I'll put in red how it often looks. I probably would say, yeah, so let F be positive, G be positive, and F and G increasing. Show that H equals to F times G is also increasing. Yeah.
Does means show the derivative of the product is increasing.
I want you to show that the function's increasing, which means I want to show that the derivative is low. Yes. I want you to show the derivative is positive. Absolutely. Good. So yeah, this is one of the major translations in this language. That when I say I want you to show a function is increasing, I want you to show the derivative is positive. That's all I'm trying to hide from you. That's all I'm trying to hide from you. Mañana is tomorrow. Absolutely, go ahead. Which two? Very clear about what you're saying. You're pointing here? Yeah, okay, go ahead. That end, all I need you to do is write that as clearly as possible. Write what you just said in a way. No dispute as to what you write. Everything you said is right. Now write in sentences so that I can't do it.
As long as the extra credit just to say this all.
Yeah.
It's just not bad to be honest.
Show that H equals to F times G.
Okay.
Show that a new function, which I'm calling the product of the two, is also increasing. This is just a comment. Oh, from above. Sorry. That's just a comment from above. Let F be positive and G be positive. Yes.
For the can you take the extra credit for proving the quotient rule using actual derivatives?
Yeah, I'm gonna actually outline that in just a second. But go ahead.
That was my question.
Okay, yeah, I'm gonna do that. Yeah. All right.
Yeah. Where's the class?
Okay. All right, I'll open the floor. Okay, go ahead.
Since H prime equals F prime G plus G prime F, and F prime G prime are never positive, H prime X must be increasing because the sum of F prime G and G prime F is also positive.
Perfect. Other explanation? Go ahead.
If F and G are positive and increasing, then the derivatives of F and G are positive. By the product rule, H prime equals F prime times G plus G prime F. And F prime, G prime, F, and G are all positive, thus their product and sum will be positive. So H prime is positive, and because H prime is positive, then the original function, or then the function H will be.
That's right. That's right. Anything else different from that? That's right. So, with 3 people have told me that in all different forms, and that again, everything that I'll open the floor to you, to those 2 explanations. Criticisms, comments.
I like how she said the product and the sum. I didn't really know that, but like.
Yeah. Okay. Okay. Excellent. Any other comments? Yeah. I mean, what they said is perfect. Shade. I know, it's all good. It's all good. Everything I've heard is great. I wouldn't take off a thing for anything that I heard. So H prime is FG prime, which is by the product rule F prime G plus G prime F. And one of the things about proofs is that when I give you, say, prove something, and I give you conditions, the conditions I give you, you need to use them all. I gave them to you for a reason, right? And so I said that F and G were positive, so that they're nice, and then F was increasing and G was increasing, so that that's nice too, so that everything here is positive. That's positive, that's positive, that's positive, and that's positive. Everything here is positive. So then it's just about writing all that stuff out in words, and you heard 2 variations of writing this very thing, and it just works out, right? That H prime is equal to the sum of positive terms. Now I'm being very lax. These should all have equal signs, okay? Greater than or equal to 0. Again, we just remember x cubed is increasing, and it does have a derivative that is 0. So greater than or equal to 0. So H is the sum of non-negative terms. And so H prime is non-negative. And so H is increasing. Go ahead. Or non-decreasing. Go ahead.
Why is it equal to 0 if we said it's greater than 0?
Say it again?
Like,
no, these also, I'm sorry, so your question again is what?
like you have greater than or equal to 0.
Yeah.
Like, isn't it just greater than 0?
No, it's a great question. And so here is the counterexample to that. H of x is x cubed, right? X cubed is increasing and has a derivative that is 0 at 0. Right? So here's an example of an increasing function that has a derivative that's equal to 0. So I need to include equal to 0. So if something's increasing, you can have a derivative that's also equal to 0. So I want to be clear. So F prime, F increasing means that F prime is greater than or equal to 0. That's what it means. Go ahead.
But didn't you say in the question that F and G are greater than 0, not greater than or equal to?
Yeah, I'm only referencing. I'm sorry. Thank you. I'm only referencing the derivatives. Yeah. Thank you. So those are okay, but in terms of derivative, it's greater than or equal to. Yeah. Questions about that? Yes, please.
Now about this now, it's you know how the derivative use a graph and you plot the derivative on it and be a tangential line.
Yes.
If you get the function y equals 2x, the derivative is 2.
Yeah.
If we were to plot that, wouldn't that cross the actual line?
The tangent line?
Yeah, like it wouldn't be tangent with it, but y equals. If you get y equals 2x as the original function,
Yeah.
the derivative of that would be 2.
Yeah.
Wouldn't that end up crossing the line and not be tangent?
You mean 2?
Yeah, 2.
So you wouldn't graph 2. 2 is the slope of the line that's tangent. 2 is the slope of the line. 2 is not the line itself. Is that okay?
Yeah.
Okay. Excellent. Please.
If you get f prime equals 0 and g prime equals 0, then h prime equals 0, but how do you know that's increasing or decreasing?
So say that again. If
f prime equals 0, g prime equals 0, so it's like 0.
oh right, this is why we're talking about a whole interval. That may be true for that particular point, right?
But then, like, how do you know h prime is increasing and not decreasing?
So how do you know that h prime is
Increasing or decreasing?
at that point or on the whole interval?
At the point.
Oh, at the point it's not.
Well, like,
At the
when it's
point.
just 0.
Yeah, if it's 0, it's not increasing at that point. We're talking about increasing on the whole. So this is good, right? So we're talking about increasing on a whole interval. So increasing on, let's say, for instance, A to B, right? So if it is the case that f prime is 0 the whole time, then f prime is constant, right? So I mean, so this is why we bring in f prime is greater than or equal to 0 on this interval. So at least at some point, so I should say it's non-decreasing. It's not going down, right? So it's not going down. So yeah, you can switch out non-decreasing if you want, yeah. But that's just a technical thing. So the point is that if we have something like this, we want to call that increasing even though the derivative here is 0, right? We still want to call that increasing. Yeah. The problem is that we don't want to call this increasing. That's not increasing, right? That's constant. Yeah. Okay. This is excellent. Good. Good. Okay. So I'll take questions about any of that. So these will come up in random places, these conceptual questions. Okay. Let me go into the book. Classic question. Number 12. Again, the book is available to you in the homework system. Let's do number 12. Yeah. Do we assume what? No, it's just what it is. Yeah. You don't have to assume it's a close number. Oh wait, well, I may see what you're saying. That's the only part of the graph that you're seeing. Yeah, it's not continuing on. Yeah, it's just that. Thank you. Yeah. Math is a language. We're just let's go ahead and translate. So all we're doing is translating this thing, horizontal tangent line. What is that really trying to say?
Or value of x is the derivative 0.
That's right. So the derivative is the slope of the tangent line. A tangent line is horizontal when it is flat. A tangent line is horizontal when the slope is 0. The derivative is the slope of the tangent line. They're really asking, where is the derivative equal to 0? Right? And so we'll do a couple of those in a second. But again, that's just more translation. So I think actually I should be able to do something nice here, right? So, oh, here we go. Here we go. So it just stopped me from creating ridiculous things. Now, one day I'll be able to actually move this where it needs to go. Move up. There we go. Almost. Right there. Ah. One last time. No, I can't even touch this thing. It's supposed to be here. Okay. And then here, right? And then here. The answers to the question: 1, 3, and 4. Questions about that? F prime of 1?
0.
0. F of 1?
1.
F of 4? 4 is 2. F prime of 4? 0. Questions about this? F prime of 2? Looks like 1, right? Looks like this slope right here. So we can at least approximate it. 2 down, 2 over. It looks like it's what? Negative 1. Good. 2 down, 2 over. Good, good, good. What values of x is the value of f the largest? The maximum is at 4. What is the maximum? 2. Right? So the maximum looks like it's in this area. The maximum occurs at 4. The maximum value is 2. The minimum value? What is the minimum value? Negative 1 is the minimum value. It occurs at 3. Good, good. As you might expect, we'll be doing stuff like this a lot. This problem, the authors are trying to make a point that for particular functions, like this red one, if you're looking for candidates where you're at the top or at the bottom, they are usually places where the derivative is equal to 0. That is to say that if you're on a hill, right, and you're at the top of the hill on a function that looks like a red function, then the derivative should be 0. This is due to, I believe it's Clairaut, or it may be Euler or Rolle. But yeah, that if you're like the red function and you're at the top or the bottom, then the derivative is 0 at those places. What do I mean like the red function? Smooth. Smooth, right? What does smooth mean?
Continuous.
No, that's good. Let's make sure that we, and it is good to find errors. That's a good thing, right? So we can clarify that. All right, one of these is smooth. One of these is continuous. I'm sorry. One of these is smooth. 2 of these are continuous. Right. So in terms of continuity, I certainly drew both of these without taking my marker off the board, right? Only one of these is smooth. The top one. Questions on that? Okay, so I'm definitely going to ask questions about that conceptually. So conceptually, there will be conceptual questions about the difference between continuity and the derivative. There will be questions about the difference between continuity and the derivative. There will be questions about the difference between continuity and the derivative. Okay, please.
Is there an actual reason why one's precise?
This is a great question. So of course the word is subjective because what's smooth for you is not smooth for me. But so what is it that we mean? So I'm giving the street version. So what we mean for smooth is then again when we zoom in on it, it looks like a straight line. right? And for these, this is not smooth everywhere because if you zoom in on this, it never straightens out to look like a straight line, right? That's the reason. Go ahead.
So the derivative at that point would be what
There
is
is
it?
no derivative.
Oh, okay.
Yeah, very good. There is no derivative. Excellent.
So this smooth is differentiable.
Differentiable is the mathematical way of saying smooth. That's exactly correct. So when I say f is differentiable, I mean that f is smooth. So that, again, on the street, you can say, when you say differentiable, or someone comes up to you and says, well, wait, someone was talking about differentiability, and you say, no, that just means it's smooth. That means if you zoom in on it, it looks like a line, right? Go ahead.
Also, like differentiable just means the derivative of both, like the limit of the
Yeah.
derivatives.
The limit of the slopes from both sides is the same, which is clearly violated at these places, right? That's exactly why it doesn't work. That is exactly correct. Yeah,
So you're
please.
saying the bottom part isn't differentiable?
It's not differentiable on the whole line.
Only on interval. Okay.
Yeah. So it's differentiable everywhere except where the corners are.
Right.
Yeah,
Okay.
absolutely. So this is good because we're clarifying differentiable and increasing at a point versus over the whole interval, right? So if I ask whether the bottom graph is differentiable on the whole real line, the answer to that is no, right? If I ask you to find where it is differentiable, it's differentiable everywhere except for those 5 places, right? Go ahead.
Okay, so you notice on the top one, there's a line. It's like a line to it. At the bottom.
Yeah, that's right. If you zoom in on it, all the way, it looks like a straight line. Yeah.
Sorry.
Yeah.
So you, when you are saying like where the bottom one is differentiable, you say it from like you do, would you do like interval and then
Yeah. That's right. Okay, good. All right, so in terms of this, here's some things that we know, right? So if f is differentiable at x, then f is continuous at x. Questions about that? The proof of that is not that difficult. Here's a sketch of it. We know that f prime of x, sketch of the proof, I should put this in a different color. Here's a sketch of the proof. We know that f is continuous if what? The limit, I should actually use a different letter. Let me think here. Oh, this is okay. We'll use this. The sketch of the proof is, we know that f is continuous if the limit as t tends to x of f of t is what?
Equal
to what?
fx.
F of x. That's what it means to be continuous. So continuous means this. I'll ask for that definition on the test. Define continuity. So that's what it means to be continuous. And so now, let's suppose, if f is differentiable, then what do I know? Then I know that f prime of x exists and it's equal to the limit as t tends to x of f of t minus f of x all over t minus x. Right? That's the definition. Now, what do I know about this limit? Does this limit exist? Does it? Why? Because f is differentiable, right? So because this limit exists, go ahead.
Oh, John, I have a question.
Okay, well, let me finish this first. So now What is it that I know about t minus x? That's going to what? 0 for sure. So what must be true about this? That also has to go to 0. So the limit as t goes to x of f of t minus f of x has to be 0. In other words, the limit as t goes to 0, x of f of t has to be f of x. And that's why it's continuous. Okay. Good. Okay, so that's a sketch of it. That's what it means to be continuous. Okay. But your question, go ahead.
Right. So when we have a rule of discontinuity,
Yeah.
we know that the limit still exists. Oh, just answer my question.
Okay. So yeah, just talk it out. Just talk it out. Of course, I'm interested in the other way. If f is continuous, does f have to be differentiable? Yes or no? No. And oh my goodness, right? The notion of mathematics as a language comes up here so easily, because if I asked the street version of this, my 6-year-old daughter would be able to answer this question, right? If I say, daughter of mine, center of my universe, can you draw something without taking your marker off the board and it not be smooth? And she says, of course. She says, of course I can do that. And yet you have colleagues, fellow students across the nation who are in calc right now and don't know the answer to that simply because of the way that it's written, right? Simply because they don't know the language. But if I ask them, draw something that has no jumps or breaks without taking your pencil off the paper and make sure it's not smooth, they could do that for days. But then if I ask them this, they're like, well, I don't know. Right? So it's purely about the language, right? That if you understand what continuity means to you in the street version, and you understand that differentiable means smooth, then this is not a hard question. And this is why, again, I keep stressing, make sure you understand the language. All right? I'm going to ask for an example. The classic example is a function that has a sharp point. That function would be the absolute value. And so the classic example is f of x equals the absolute value of x. That is a function that we will graph. The absolute value of x is what? What is the absolute value of x?
V-shape.
It's a V-shape. Why? Because we define it to be
If x is less than 0.
if x is greater than or equal to 0, what is it? It's just x, right? So that the absolute value of 7 is 7. You do nothing to it, right? So the absolute value of x is just give me the number back if it's positive. If it's negative, then you need to change the sign, right? So that the absolute value of negative 12 is negative 12. You change the sign and it makes it positive, right? So that's the definition of the absolute value. It's a piecewise function. And obviously when you graph that, over here it looks like x. Over here it looks like minus x. That's why it looks like a V. No derivative at 0. It's pretty obvious why it's no derivative at 0, and it's to Camilla's point that obviously the slope's moving from the left. What's the slope coming from this side? What's the slope of this? 1. What's the slope here? Negative 1. There is no unique tangent line here. Okay, good. There's some other funky functions, right? Like x to the 1/3. There we go. X to the 1/3 is defined on the whole real line. X to the 1/3. That thing there. Now the great skeptic comes in and she's about to kick my butt for sure. locally looks like a line, doesn't it? It's just vertical. Right? It's just vertical. So derivative here is undefined. Right? So I've been lax. So it needs to look like a non-vertical line. The tangent line should be non-vertical, right? So, and this makes sense, right? Because what would we say about the rate of change at that point? The rate of change is infinite, right? If we wanted to use the extended real line and define a derivative at this point, we would say that it's infinite, right? The vertical line there, okay? So actually the third is also an example of a function that is continuous. It looks beautiful, right? No derivative at 0. Right. Questions about that? Okay, excellent. Anything else that's interesting? I guess we should practice this difference quotient thing at some point. We'll do that when we practice for the test. 21. There are some functions, ridiculous functions, that are continuous everywhere, no derivative at any point. Continuous but no derivative at any point. And those are super funky. You might imagine that those functions have spikes all over the place. As a matter of fact, they have spikes everywhere. They have spikes everywhere. Imagine that. Go ahead.
Couldn't you still find the derivative at some point, even if like you had spikes everywhere? Because I feel like because you're trying to find the derivative you're trying to find like in that first function, the spiking one, right?
Yeah.
You could find the derivative of that first part, like that first section.
Yeah.
Right, without the spikes, right?
That's correct.
Because you don't need the spikes.
That's correct.
Right?
That's correct.
So, how could you, like, I feel like the only way you could not find the derivative if the graph was like, unless the graph was like a collection of points.
Well, right. So there's a way of approximating that. So first of all, the function I'm talking about, like, you would be introduced to it in your senior year of being a math major. That's number one. It's a very outrageous function, right? And so, but the way that you come up with it is recursively. So you would take that, right, and then solve the very issue you said, is that, well, it looks like that you can take a derivative somewhere on that interval, and then you put a spike on that interval.
Oh my god.
And then you put a spike. So all of those flat spaces, you just start filling in spikes, and then you take the limit, and then there's spikes everywhere, right? So so you start just throwing in spikes at all the places where it's smooth, right? And so so you're talking about something that, again, locally, it just looks like, it's like, and then of course what you want to say is that, oh, well, let's zoom in on it. Yeah, I know, right? But no, it's set up so that, So I'll bring that function, or we can talk about that function at some point. I just have to come to the office hours and talk about a whole bunch of degenerative examples like this, right? So I got to talk about this function. I got to talk about, there's something else I needed to talk about. Camilla, what did we need to, why 1 plus 1 over n to the n power, why that's always less than 3, right? So I got to do some induction stuff. So I'm going to come to office hours or come to study and just talk about some crazy stuff, right? That's a lot of fun. Go ahead.
Like if you have x to like
like raised to a fraction, is it always not differentiable at x equals 0?
That's a great question. So I don't know that's true. That's true. Yeah, no, that's always true, right? And so, but that fraction has to be less than 1. Yeah. So she's making the point that if alpha is between 0 and 1, then x to the alpha is not differentiable at 0. And what's great about this thing here is that we can at least get some intuition on that. If I call that A and then I want to slide A, can I affect the slider? I guess I can, right? So then, see, there we go. So it just doesn't look like it's nice, right? So for none of these values of A, does it look like you're having a derivative at 0? None of these values. And I'm just taking A between. Oh, can I change this? Oh my God. So 0 to 1. Can I leave the step out? Oh, just outrageous. No derivative for any of those at the origin. Oh wait, what's that one? That still doesn't look like it works, does it? What in the world is special about 0.76? They won't even let me zoom. I don't know. So this is good because I think this is a programming problem. Right? This is an issue with the programmer. However this has been programmed, it looks like it works, but you can demonstrate that there's no derivative here either. Right? That's supposed to be vertical. That's supposed to be vertical.
That's what I thought of. I was like, oh my god.
What?
No, because when you get the absolute value thing on the board, all
Yeah.
you do is programming and how you're programming the absolute value. You've got to split up into different functions.
Yeah.
And then,
Yeah, no, yeah.
I was like, I was looking at this.
Okay. Oh, so here's a classic example of how how we cannot rely simply on what the calculator tells us. Right? Because if you rely on that, then yeah, you're gonna run into problems. Okay, we'll end there. Next time we will start talking about the chain rule. The chain rule. Anyone got any songs for that? Inside, outside? I have no idea. I think I'm going to freestyle about the chain rule.
The chain rule makes me cry.
What did you say?
The chain rule makes me cry.
Oh no, not anymore. Not after tomorrow. No.
It's just, when it's like really small, I'm just like,
Yeah, I know, right? Yeah.
And I'm just always talking to my EMB and teachers.